Catalytic decomposition of methane to obtain hydrogen with catalyst synthesized from sewage sludge from the galvanoplasty industry. The authors are Montero Calderón, Montúfar, Gavilanes, Moreno, Solís, Montes de Oca, and de la Rosa from Universidad Central del Ecuador, and the speaker is Hugo Solís. 14:30. La de arriba, 14:30.
No. Does that work? Okay. Okay. Good afternoon, everybody. My name is Hugo Solís. I'm from Quito, Ecuador, and I'm a researcher of the Central University of Ecuador. And today, we're going to talk about the catalytic decomposition of methane to obtain hydrogen with catalysis synthesized from sewage sludge from the galvanoplastic industry. This work is a collaboration with Montero, that is the first author, and the co-authors Montúfar, Gavilanes, Moreno, Solís, Montes de Oca, and de la Rosa. This is the contents of this presentation. And first of all, we're going to start with a short introduction. As we know, the hydrogen is very important in different industries, as refinery and the energy, new energies. So I show you different methods to obtain the hydrogen. The first one is the steam reformant, that is very common in the refinery of oil. The second one is the thermal decomposition of methane. That is, well, this method is has a disadvantage because it needs a lot of energy, approximately high temperatures, and we are going to focus in this method about the catalytic decomposition of methane, the CDM. So it's a new technology, and in the main objective of this work is establishing the model and kinetic parameters of the CDM reaction uses a catalytic derived from sewage sludge from the galvanoplasty industry. And for the experimental previous the selection of the catalysis, we discriminate, we use a bank of sewage sludge. So we use the technique of the TGA in order to determine basically the desactivation of the catalysis. So the best catalysis that we use for this work is the catalysis named CIN, the CC, and the CG. So as you show in the table, so we see some different properties of the superficial area and the percentage of metallic on the catalytic surface. So for example, the catalysis CN has the most iron. The iron is approximately 40%, and the CC, the calcium is the highest metallic, and in the CG is the zinc. So with these three catalysis we use for our experimentation. And what we do, so basically we use all the amount of the sludge. so we don't need to do a supporting catalysis. So only we put the amount of the mass of the catalysis, and we prepared using a calcination with these conditions. After that, we prepared an extrusion like a pill. The weight of the pill is 1 gram. The diameter is 25 millimeters, and the thickness 1 millimeter. So after that, before to do the reactions, we do a catalytic reductions with these conditions using hydrogen. So, and we put the catalysis in this basket. This basket is of the reactor. We use a batch reactor, and this reactor has a temperature controller where we can manipulate the temperature. And after that, we do experimental design where we change the catalytic mass and also the temperature. With that, we choose the best catalysis. So first of all, we work with changing the temperature. We work with 350 Celsius degree, 400 Celsius degree, and 450 degrees. So in the first stage, we maintain the catalytic mass constant. So, and with these results, we obtain the best catalysis. And for the best catalysis, we do the second part, that is changing the mass of the catalysis, but maintain the temperature constant. So, and after that, the last experimental was to compare our catalysis with with a commercial rhodium catalysis at the same conditions of the second part of the experimentation. So, to get the data, to get the information, basically we use the data of the pressure that we got in the reaction, and also we use the TGA method in order to determine the desactivation of the catalysis, and also we use the gas chromatography in order to analyze the compounds or the products that was formed in the reaction. So in this part, I'm going to show you only the most important results for the time. So, for example, we can see the results of the reaction using the reactor at 450 Celsius degree, and the different catalysis that we use. The first one is without catalysis, and the second one, the blue, is with the rhodium catalysis. The tier one is the CN catalysis. Okay, so as we see, for example, in this part, we can see how the total pressure of the reactor is changing as function of the time. It's because the reaction is producing inside the reactor. And in this picture, we can see the same reaction, but changing the mass, the catalysis mass. We have for 2.5 grams, 10 grams, and 5 grams. And also, in this case, the pressure, the total pressure changes as a function of the time. So in this case, for example, we got the best result using 10 grams. And with all the data of the pressure that we got of the reactor, we do pressure balance in order to determine the kinetic. So for that reason, we use the integral method in order to linearization this data, and we graph basically the inverse of the pressure as a function of the time, and we got the equation. So we did that for all the reactions, but to get the model, obviously we use the best conditions. And after that, we determine the conversion at the function of the time for the different temperatures using molar balance. And as we see, the best results for the conversion is for the temperature of 400 Celsius degree. With this data, we determine the kinetic model. Is a very easy kinetic model where we establish the value of the constant, and we determine that the reaction has a behavior of the second order. And to verify and demonstrate that this equation is good, also we can call this model the experimental model, but we compare with the Lagrange-Hiselwood criteria in order to determine a theoretical model. So for that reason, we must to do the mechanism of reaction, and we select, we must to combine different assumptions in order to obtain the concrete mechanism that was in the screen. So, for example, we're going to assume, for example, the kind of absorption, or maybe the type of the superficial reactions. So, but it was the best concrete model. And after that, we determine the rate limiting step. So for that reason, obviously, we must to assume the different limited step for the superficial reaction, the desorption, and the absorption. And for the best data, so we determine that the absorption is the limiting step for the reaction with this catalysis, and we got the same equation. So we demonstrate with the Lagrange-Hiselwood criteria and the experimental data that we got the same model. So in this case, we determine the kinetic model, the mechanism of reaction, and also the limited step. And with this data, also we calculate the activation energy and the frequency factor. For that reason, we establish the parameters, the kinetic parameters for the reaction that you can see in this screen. And also we determine the kinetic constant and the frequency factor A and the activation energy E. And after that, we took the samples of the products using a hermetic bag, and we analyzed in a chromatographic analysis. So you can see here the different composition of the gases at different temperatures. For example, hydrogen for the CN catalysis at 350 is 71%, and for the other ones. And also, you can see the analysis of the best catalysis using, compare with the commercial catalysis, that is the rhodium. So, as you see, basically we got the same conversion of hydrogen, and it's very good because we are recuperate the sludge, the sewage sludge, that if we compare the economic part, for example, with the rhodium catalysis is very expensive. And after that, we compare the results of our model, the first one, with another authors that work with with different sewage sludge. So you can see the different type of reaction with the different catalysis and different conditions that another author use. So, for example, in our case, we got a maximum conversion of methane of 24% at 400 degrees using iron, and others authors use nickel, supported in alumina and titanium. And this one also we compare with other authors that we can find. As conclusions of this work, for example, the CN catalysis produce more hydrogen in favor of the reaction. The maximum conversion occurs after 1 hour of reaction, and the optimal temperature for this process using this catalysis is 400 degrees. And using the chromatography, the optimal amount of CN catalysis is 5 grams, because there is a production of approximately 71% of hydrogen, and that is the higher than the 69% that was obtained using 10 grams. And the kinetic models, this is the parametric data, the square R 0.99, and a velocity constant at 400 of 0.00593.5. The methane conversion using this catalysis was of 24%. The frequency factor and the activation energy, you can see these values. And the limiting step of the CDM in this molecular absorption of methane is the absorption, and also the 450 degrees with 2.5 grams of catalysis of CN, there is a mass loss of 228, which favor the formation of carbon. And the CN catalysis presents a molar hydrogen production of 71% of CDM, that, as I said, is very important for the cause of the rhodium catalysis. And that's all. Thank you very much. This is the bibliography. And if you have any questions, thank you.
Your byproduct, your secondary product is carbon, solid carbon.
Yes.
Deposited over the catalyst.
Yes, we analyzed the desactivation, but in this presentation I didn't do that. But yes, the problem of the reaction is that we got a lot of carbon. So it's a problem in the desactivation. We must, for example, to do in an industrial plant, for example, maybe a fluidization in order to attack this problem. Mm-hmm.
Do you verify or check if your reactor is active?
The reactor?
The reactor.
It's a batch. It's a batch reactor. Yes. So,
Do you verify if the walls of the reactor are active for your reactor? The baskets?
Well, the basket is from. No, it's the material is good. Is steel. Carbon steel. So I don't know that this material influencing the reaction. Mm-hmm.
Only thicker alloy does not cause the carbon precipitation.
Maybe it's a good question. Maybe we need to use this information for the next step for the research. Mm-hmm.
Why did you select the temperature 450 degrees. How about that? 500 or 400 degrees? The decomposition rate increase or decrease? Which one?
So it's very interesting your question. So for this case, we show different papers and we use the same condition of different articles. But in this case, for example, the best temperature, in order to get a production of 71% of hydrogen, is the first one. Obviously, it's because it has the highest content of iron.
Iron.
Mm-hmm. Yes. Mm-hmm.
Iron is the most important for catalytic species.
In this case, yes. Mm-hmm.
And how about an increase in temperature of 500 degrees that get an activity of iron component is right or no?
So yes, the problem is here that we increase the temperature, we start to increase also the carbon. So it is very difficult because the catalysis is going to deactivate. Mm-hmm. Okay.
Last question. May I ask you, how did you ensure that at that temperature and considering everything, there are not any diffusional effects that are being not considered in the velocity constant?
So for that, we do this equation. So in this case, also we use the Arrhenius equation with the data that we obtained from the reactor, principally the temperature and this constant, in order to to calculate the activation and the frequency, the activation energy and the frequency factor. So yes, maybe we need more data or more information to compare. Yes, but also we use that with some, for example, the reaction at conditions of 25 Celsius degree that we can got in a book, for example, and with data and with the data of the reactor we can determine the cinetic also.